Alrighty, hello and welcome to the Tuesday edition of Chem 305. We're going to keep rolling. Oh, goodness. Rolling today with solutions. The solutions to all of our problems. I don't think I have anything by way of announcements other than I've started outlining our third exam, just trying to get a little ahead of the curve there. I should be posting more information about an outline so you know what chapters it'll cover, exactly what concepts from what chapters, and the point outline that I normally do. So that should be landing a little sooner than normal. Other than that, I don't have any announcements. Okay, so last lecture ended rather abruptly, mostly because right as lecture was ending, my wife's car ran out of gas, so I had to split rather abruptly to go help her out. And so I wanted to open this lecture with an example problem that's very similar to the example we closed with. It's kind of an atypical, or it was a different, what's the word I'm looking for? The problem itself was a little different than the ones we normally do, and so I wanted to work a second example together so that, because I like finished it, I'm like, boom, there's the answer. I gotta run because my wife has no gas in her car and it's 187 degrees outside. But we're gonna do a similar example problem now, and if you have questions at the end, you can hit me with them. And so hopefully it'll solidify this type of problem in all of your minds. So let's do the following example. A solution of aqueous ethanol has a percent by volume of 40.0%. All right, that's the percent volume to volume. Determine the percent mass to volume if the density of ethanol is 0.789 grams per mil. All right. Now, to do this problem, you have to conceptually remember what this 40% means. All right. That 40% by volume literally means that you have 40.0 grams of ethanol, which I'm just going to abbreviate as ETH, in every 100 grams of solution. All right, that's what that 40% means. Okay, and what we're being asked to find here is the percent mass to volume. Wait, hang on. I messed up. It does not mean 40 grams over 100 grams, right? Because here we're dealing with percent volume, not percent mass. So this is actually 40.0 milliliters of ethanol per milliliters of per 100 milliliters of solution. And so this is, what it means. We want to find the percent mass, which is grams of ethanol over milliliters of solution times 100%. Here, hang on one second. I'm gonna go ask them to be a little more quiet. Yo, Joe! You need to whisper, because your voice is coming through the class. So whisper. All right, sorry about that. My dream for this summer session is to have a week where that doesn't happen. I don't have to go out there and ask someone to be more quiet because it's coming through the walls. Okay, so anyways, this is what we're shooting for. We want the percent mass to volume, and we're given percent volume to volume. Now you'll notice we have the correct units in our denominator, right? Milliliters of solution. Where this is, what needs to change is the numerator, because right now we have milliliters of ethanol, and what we want to end up with is, oh good, oh good, you're good. Okay, that's awesome. Maybe it's just maybe it's these headphones, where I'm like, I hear their little tiny voices. But if you can't hear it, that is good. That's all that matters, really. Okay, so we need to convert from milliliters of ethanol to grams of ethanol, and we can do that conversion using the density, right? So we want a unit conversion that is going to cancel milliliters of ethanol and leave us with grams. And the density tells us that there are 0.789 grams of ethanol in 1 milliliter. So if we multiply this expression by the density, grams over milliliter, milliliters of ethanol cancel, and now we're ready to crunch our numbers. So we have 40.0 times 0.789 divided by 100, and this equals 0.3156. But now you'll notice, so first a couple things. Sig figs wise, we can only keep 3, right? 3, because our percent volume only had 3, and then our density only has 3 sig figs, so we can only keep 3. But second, you'll notice that this answer right here is a decimal, and what we want our answer for our answer is a percent. So we need to multiply our decimal by 100 to turn that decimal into a percentage. So when we do, we find that the percent mass to volume of a 40% volume to volume solution of ethanol is 31.6%. All right, so there is a second. Okay, say you have oh gosh, you have fox-like hearing. All right, so that's an example similar to the one we closed with last time. Basically, whenever you're given a percentage, whether it's percent volume to volume, percent mass, all that stuff, you can assume whatever that percentage is, that many, if it's volume to volume, milliliters over 100 milliliters, or that many grams over 100 grams if it's percent mass to mass, because that's literally what that percentage means. Okay, so that is a similar example to the one that we ended with. And so as of right now, okay, yeah, Brianna, you too. So as of right now, we have learned several concentration units. All right, several concentration units. Just by way of just review, we know percent mass to mass, percent mass to volume, and percent volume to volume, right? These are the three concentration units. But the most important, right, so we've learned all three of these. The most important unit, concentration unit, however, has yet to come into play, and we're going to start talking about it now. The most important concentration unit is molarity. All right, molarity is far and away the most important concentration unit. It is abbreviated with a capital M. All right, and molarity, the equation for it, is equal, to moles of solute over liters of solution. All right, moles of solute over liters of solution. This is the one that chemists love because it has moles, and anytime you have moles, you can do stoichiometry. So this links all the concentration concept we've been talking about to all of the stoichiometric calculations, percent yields, all that stuff that we have been that we've been learning up to this point. All right, it's pretty darn cool. Something you should know. By the way, so when you have, let's say you have 1.0, and then the molarity unit of sodium chloride, let's say this is your solution. The way you say it is you say, if you were to say this, you'd read it 1.0 molar. So you'd say a 1.0 molar solution of sodium chloride. So that's how you would read that. If you're reading it on the page, you'll hear me say that as I'm teaching. We have a 3 molar solution or a 0.46 molar solution. That's what that means. Whenever you hear molar solution, the unit that we're talking about is the unit of molarity. All right, so let's throw this thing into the mix and start working some problems. All right. First, let's do an example that's similar to the last two that we've done. All right. So concentrated hydrochloric acid, which is HCl. Let's see. There we go. Concentrated HCl has a percent mass to mass of 37%. The density of the solution is 1.010 grams per milliliter. What is the molarity of this solution? All right, now notice we have been given percent mass, right? That tells us that we have 37 grams of HCl in 100 grams of solution. All right, and we are being asked to find the molarity of HCl, which is equal to moles of solute, which is hydrochloric acid, over liters of solution. So you'll notice we have two problems, so to speak, two things we need to do a conversion on. We need to convert our denominator from grams of solution to liters, and then we need to convert our numerator from grams of HCl to moles of HCl. Well, we can do that first unit conversion, right? Well, which one do we pick first? We can do either first. I'm going to choose to convert from grams of HCl to moles. And to do this unit conversion, we're going to need to calculate a molecular weight. All right, so hydrogen has an atomic mass of 1.01. Chlorine has an atomic mass of 35.45. So when we add these two together, it'll be 36.46. All right, so we have, for every 1 mole of hydrochloric acid, we have 36.46 grams. All right? So grams of HCl will cancel with grams of HCl. Now our numerator is what we want it to be, right? It's in moles. Now we need to work on the denominator of this expression. We have grams, we want liters, right? And the density will not tell us how many liters, but at least it converts it to a volume, right? If we want to cancel grams of solution, we put grams of solution in the numerator. We want to be left with milliliters. And the density tells us that there are 1.010 grams of solution in 1 milliliter. All right? That cancels grams of solution with grams of solution, and now we're almost there. We're almost home free. We're not quite there, though, because right now we have milliliters in our denominator, and we want to land on liters, so we have one more unit conversion to go through. We want to cancel milliliters of solution. We want to be left with liters. And we know that 1 milliliter is 10 to the negative third liters. So now milliliters of solution cancels, and we are ready to crunch our numbers. So let's take a look. So we have 37 divided by 100 times 36.46 times 1.010 divided by 10 to the negative third, which is actually just times. Wait, hang on. 37 divided by 100 divided by 36.46 times 1.010. There we go. Divided by 10 to the negative third. All right, and this, the number that we're getting is, or that I'm getting, is 10.2496, right? But we can only keep 2 sig figs because our initial percent mass only has 2 sig figs. So we keep our first 2 rounds down. Here's the problem. our answer cannot be 10 because 10 only has one sig fig, right? We've got to write this number in scientific notation as 1.0 times 10. That is our final answer. All right, so that is an example of how you can take a concentration in percent mass and convert it into molarity. That could be one type of problem that you could run into on the exam. Another type is an example that I'm going to write out, but I'm not going to do this one. I'm going to leave this one with you to see if you can solve it. All right. So consider the following reaction. Let's see. Aqueous silver 1 nitrate reacts with aqueous calcium chloride. So this is also aqueous. To produce silver 1 chloride, which is a solid, and calcium nitrate, which is aqueous. All right, part A. Is write a balanced chemical equation. Part B is if you mix 25.0 milliliters of 1.00 molar solutions of each reactant, what would the percent yield of the precipitate be? And then part C. Sorry. Here I wrote percent yield. I meant to write theoretical yield. Theoretical yield. And then part C, the percent yield is 87.3%. What was the actual yield? All right, so give this problem a shot. Take a try, take a crack at it. Maybe we can talk about it in office hours later, but give this a go on your own, and see how it goes. Bring it up in office hours if you're struggling. But this is a this problem right here. You should know is exam caliber. All right. Okay, so moving right along. Let's take a moment to talk about dilutions. All right, dilutions. The process of dilution is very, very common in a chemistry lab. If you ever work in a stockroom, this is like 90% of your job. Is diluting solutions, and what dilution is, simply put, is dilution is adding water, or I should say, adding solvent. Doesn't have to be water, but adding solvent to reduce the concentration of a solution. So, for example, with when our stockroom buys hydrochloric acid, for example, or let me dial it back one more step. In an experiment where, let's say, you need hydrochloric acid to do in an experiment. Let's say that you need for a lab, let's say students are going to be doing a lab where they need 2.00 molar HCl. All right, so they need a solution of HCl that's 2.00 molar, and let's say that that for all the students to do the experiment, let's say that we need a total of 500.0 milliliters of it. All right. Now, we do not. The stockroom does not have 2 molar HCl in the back room. All right, we don't have that stocked in the stockroom. What we do have is concentrated HCl, is 10.24 molar HCl. All right, and what the stockroom does is they have to take that concentrated HCl and then dilute it down so that the concentration is the correct amount, right? So we need to know what volume, how many milliliters of concentrated HCl do they need to use to make 500 milliliters of 2 molar HCl. And the way they figure that out, the way they determine that, is with the dilution equation, which is initial concentration multiplied by the initial volume is equal to the final concentration multiplied by the final volume. All right, and just to be clear here, M1 and M2 could be any concentration unit. It could be molarity. It's molarity in this problem, but it could be percent mass. It could be percent mass to volume or percent volume. It can be any concentration unit as long as they are the same concentration unit. Similarly, initial volume and final volume could be any volume unit as long as they're the same. All right, so in this problem, M1 is that concentrated HCl, that 10.24 molar. M2 is what we need. It's the 2 molar HCl. Or I guess I don't know why I didn't include HCl in the box. And then I wrote V1 here. should be V2. Oh! Sorry, Jen, I just saw your question. My decimal place is very small. So yeah, that's 500.0 milliliters. And that final volume V2 is the 500.0 milliliters. So we have everything we need to solve for that initial volume, that volume of HCl that we need. So rewriting our equation, M1 V1 equals M2 V2. Yeah, totally. Or total with two L's. All right, so we have to isolate initial volume on one side of the equation, so we divide both sides by our initial concentration. Molarity cancels, and we get initial volume is equal to our final volume, final molarity times final volume over initial molarity. Now we have all these. Our final molarity is 2.00 molar, final volume 500.0 milliliters, and initial molarity 10.24 molar. You'll notice that molarity cancels. Our only unit left standing is milliliters, which is good because we're solving for a volume. So we go 2 times 500 divided by 10.24. Gives us an initial volume of, and let's see, we can only have 3 sig figs here because of our limited by our initial molarity. So we need 97.7 milliliters of concentrated 10.24 molar HCl. All right, so that is the amount of HCl that we need to start with to dilute to 500 milliliters. If I asked you the question at this point, hang on. Here, if I ask you, at this point, I could ask you, how much water is added to the 10.24 molar HCl? Well, here, to answer this question, how much water is added to the concentrated hydrochloric acid, we have to use both the initial volume, which we just calculated, and the final volume to take the difference. The way you get from 97.7 milliliters to 500 is you've got to add a bunch, right? The amount that you have to add is like so. So we know that our total volume is equal to the volume of HCl solution plus the volume of H2O added. And the thing is, we know this one because it's our final volume, and we know this one because it's our initial volume, right? So we have 500.0 milliliters is equal to, that's our total volume, is equal to our 97.7 mils plus the volume of water added. So to find that, we just have to subtract 97.7 mils from both sides of this equation. So we get 500.0 minus 97.7 tells us that the volume of water we have to add, or that we did add, is equal to 402.3 milliliters. You'll notice we do not need to mess with our sig figs because both of these numbers have their last significant digit in the first decimal place, and our answer does as well. So this is our final volume. Or sorry, not our final volume. This is the volume of water we added to our concentrated hydrochloric acid to make the 500 milliliters of 2.0 molar HCl. All right, the dilution equation. So that is the dilution equation. It's not too horribly bad. It's pretty straightforward. It's you know, you got 4 things. You're given 3. Solve for 1. And there's plenty of practice with that in our homework. Okay, at this moment in time, we have finished with all of our all of the math really involved in chapter 8. All right, we've done all of the heavy lifting, so you now can tackle all of the homework problems that involve any calculations that you'll be tested on in chapter 8. We just have a few conceptual things to go over. I went a little out of order with the way the book presents the information, but I wanted to kind of get the algebra out of the way first. So now we just have to talk about some conceptual things, starting with solubility rules. All right, we've already seen that different compounds have different solubilities in water. Kind of the example that we've used the most is comparing sodium chloride to silver chloride, right? For sodium chloride, you can dissolve 0.36 grams of sodium chloride in 1 gram of water. All right, and for silver chloride, you can dissolve a ton of sodium chloride. You can barely dissolve any silver chloride in H2O, right? You can dissolve 0.000002 grams of silver chloride in 1 gram of water. All right, and it's so little, it's almost non-existent. We would call, because this is so small, we say that silver chloride is insoluble in water, which means it doesn't dissolve. Like, technically a very small amount does, but it's so small that it's just considered insoluble. Whereas sodium chloride, on the other hand, we say that this is soluble in water. Water can dissolve sodium chloride. All right, and they're different ionic compounds. All of them have different solubilities, but they can kind of be broken down into these large categories. Like, if you have this type of ion, it's considered soluble. If you have this type of ion, it is not considered soluble. And those are our solubility rules. These are general categories. General categories that we we're about to dive into. All right, so normally I would say that I would encourage, well, not encourage, under normal circumstances, I required classes in the past to memorize the solubility rules. But because we're online, you can just look them up, right? You know that every exam is open book, open internet, open other humans. So I would suggest making like a cheat sheet and having the solubility rules written down, or having the page of your textbook open to the solubility rules when you take the next exam, because they'll definitely be on there. And if you don't have it memorized, at least have this for a quick reference. All right, this is I think I wrote down the page. Yes, so you can find the solubility rules on so you can find them on page 210. In chapter 8 of the textbook. So when you're taking the exam, either have this open or maybe make a little smaller, more portable version that you can have with you for taking the test, because they'll definitely be on there, and you don't want this to take a ton of time. All right, so the first category of ions is a category I call always soluble. All right, these ions are considered to be always soluble, and they are lithium, sodium, potassium, you'll notice our first column there, ammonium, NH4, always soluble, and acetate, C2, H3O2, also nitrate, NO3. These are our always soluble ions. If they're in a ionic compound, that compound will be soluble. And when I say soluble, by the way, what I mean by soluble is that that ionic compound will be in the aqueous phase. All right, if these are there, it will be in the aqueous phase. Contrasted with the always soluble list is a list of ions that I call the usually soluble. And again, soluble means that these ionic compounds will be in the aqueous phase. Usually soluble ions include chloride, bromide, and iodide. Now, I said these are usually soluble, but you should know that they are insoluble, which in other words means that if paired with these ions, they will be solid precipitate. These are insoluble with silver 1, lead 2, and mercury 1, which is a polyatomic ion. So if chloride, bromide, or iodide are paired with any of these, they're solids. Otherwise, they'll be aqueous. All right. Another usually soluble ion is sulfate. All right. It will be aqueous unless it's paired with one of these insoluble. It is insoluble when paired with one of these cations. Hang on. Okay. Hold on. Photoshop's being a little bizarre. Oh! Okay. Sorry, no, sorry. My finger had turned my opacity down to 0, so I was drawing, but it wasn't copying. Okay, we're back on track. So, sulfate is usually soluble, but it's insoluble when paired with calcium, strontium, barium. This is SR, by the way. That looks like SM. I'm going to redraw that. Barium, that again looks like an 8, that's a +2. Silver, and lead, 2. Alright, so those are the always soluble, the usually soluble. Next, we have a group that I call the always insoluble. Always insoluble ions. There's just 2 of them. Carbonates. So carbonates are always insoluble. Phosphates, always insoluble. And again, insoluble means that they will be in the solid phase. And then you have a group called the usually insoluble. Usually insoluble ions are hydroxide and sulfide, but something to note is these ions are soluble, which means they'll be in the aqueous phase when paired with calcium, strontium, and barium. All right. So these are the solubility rules. In the book, they're broken up slightly differently into the table, but all the in the solubility rules table, it's broken up a little differently, but they all fall. Both ways will lead you to the right answer, just different ways up the mountain. Now, there is a paradox. There is a contradiction on this slide, and the question is, what happens when you take an always soluble ion and pair it with an always insoluble ion? Right? What would happen if we put lithium together with carbonate? Because carbonate's never soluble, lithium's always soluble. And the answer to that question is this. It's exactly what happens when an unstoppable force collides with an immovable object. Right? It's a contradiction. One of them has to give. And in the solubility world, the always soluble always wins. So if you pair an always soluble with an always insoluble, it will be soluble. If you pair an always soluble with a usually insoluble, it'll still be soluble. So the solubility wins over insolubility when it comes to the always soluble ions. Cool? Okay. Let's take these and start applying these solubility rules. So, for the next several examples, questions, let's determine the solubility in water of each ionic compound. All right. So so let's look at lithium sulfide. All right. Now, sulfide is usually in Sol. It's usually insoluble, but lithium is always soluble. All right? So that means that lithium sulfide is soluble. All right? Anytime you have one of your always soluble ions, your compound will dissolve in water. They win every time. All right? Looking at, let's do another example. Looking at barium iodide. Now, iodide, first off, barium right here is not listed. All right, barium as an ion doesn't fall under usually soluble, usually insoluble, no information there. So we are going to have to determine whether or not this is soluble based off of iodide. Now, iodide is usually soluble, which means we have to look up when it's insoluble. All right, and iodine is insoluble with 3 ions. Right, silver, lead 2, or mercury 1. Because barium is not on this list, right? Barium is not any of these. So that means that this is soluble. If barium had been on the list of the exceptions for our usually insoluble ions, it would be insoluble, but since it's not on the list, it's soluble. All right? Let's do another example. Let's do lead to bromide. All right? Now again, bromine is usually soluble. All right? Usually soluble. It is usually soluble. It is only insoluble. Again, looking at the list, if you don't have it memorized, it's insoluble with silver 1, lead 2, and mercury 1. And what you'll notice it's insoluble with lead 2, and that is the ion that we're paired with. So this is insoluble. Bromine is usually soluble, but this is paired with one of the exceptions. All right? Let's do another example. All right, NH4Cl. One of the things you want to train yourself to do is identify your always soluble. Your always soluble ions, because if they're there, then you don't have to think about it. It's automatically soluble if you have one of the always soluble ions in the compound. All right? So that's just a really good kind of set of ions to know because they're easy and they will make your life easy. All right, let's look at this. Now, the first time I start throwing transition metals at students over solubility problems, they can start to kind of like worry or freak out because they're like, you didn't talk about transition metals. And that is correct. I didn't talk about transition metals at all, which means that you should be able to determine the solubility based on the other ion. All right, you can expect me to throw transition metals in the solubility rules questions on the exam, because you just have to look at the other ion and then figure out your solubility based on that one. So, let's talk hydroxide. Hydroxide is usually insoluble, all right? But there are exceptions. There are exceptions. Hydroxide is usually insoluble, but it is soluble when paired with calcium, strontium, or barium. You ask yourself, is iron on that list? The answer is no. That means, since iron is not calcium, strontium, or barium, because we have an hydroxide, this compound will be insoluble. It will not dissolve in water. Because hydroxide is usually soluble, and iron 3 is not on its exceptions list. All right, let's do a couple more. Silver nitrate, again, your always soluble list is your best friend. Nitrate is on the always soluble list. That makes silver nitrate soluble in water. All right. It also makes silver nitrate the bullets that they use in Underworld, that the vampires use for shooting werewolves. They're filled with silver nitrate because the silver will burn the werewolves from the inside out. Now you know that it's also water soluble. Let's take a look at calcium sulfate. Now, calcium ions are not found explicitly in a category of soluble, insoluble, but sulfate is on our usually soluble list. All right, it's usually soluble, which means it's only insoluble with a few specific ions. So here, calcium sulfate is insoluble when it's paired with, sulfate is insoluble when it's paired with calcium, strontium, barium, silver, and lead 2. All right, and because even though sulfates are usually soluble, because calcium is on its insoluble list, we then say that calcium sulfate is insoluble in water. Here, let's do another one. Let's do a terrifying one. Cr2 parentheses CO3. Oh, let's clarify that. CO3 close parentheses 3. All right. Now, carbonate is on the always insoluble list. All right. Carbonate's on the always insoluble list. That means it's only soluble if it's paired with an always soluble ion, and chromium is not on the always soluble list. Because it's not, that makes this compound insoluble. All right. Anytime, now again, here's another transition metal, right? Chromium. Anytime you're given a transition metal, don't freak out. That's just my hint to telling you to look at the other ion. That ion will determine whether you're soluble or insoluble. Cool? Let's do one. Now let's do a couple more examples. We'll do 2 more. So first, let's look at Na3PO4. Sodium is always soluble. So it does not matter what it's paired with. It doesn't matter that phosphate is always insoluble. Since sodium is always soluble, it wins. So this compound, sodium phosphate, is soluble in water. All right, let's look at another one. Let's do nickel 2 chloride. Again, we don't know anything about nickel. That just means look at the other ion. Chloride is usually soluble. Usually soluble, and it is insoluble when paired with silver, lead 2, and mercury 1. All right, that's when it is insoluble. So, because nickel is not on this list, that means that nickel 2 chloride will be soluble in water. All right, these are the types of solubility problems, solubility rule questions you can expect to see on the exam, which drops a week from Friday. All right. So we just have a couple more kind of conceptual things. Something that I want to mention more in passing than anything else, just to give you the vocabulary so you know what it is. The book spends a little bit of time talking about colloids in this chapter. And a colloid is very similar to a solution. It may look almost identical, but it's actually a different thing. So a colloid is you get a colloid when you have small particles I should say small, not just small particles, but small insoluble particles suspended in a liquid. I can't call it a solvent because it hasn't dissolved the stuff. It's just small insoluble particles suspended in a liquid. All right, so that's what a colloid is. And an example of a colloid that you all are familiar with is milk. Milk is a colloid. There's a fine dusting of calcium particles that are suspended in the solution, or sorry, not in the solution, in the liquid, but those calcium particles have not actually been dissolved by the liquid water. They're just floating in solution and they never settle to the bottom. That's what a colloid is. Now, we've got two last things to talk about in chapter 8. I don't think we're quite going to finish them, but I'm at least going to start. One is something called Colligative Properties. All right, and colligative properties. The idea behind colligative properties is this: when you add or the act of adding solutes to a solvent changes the properties of that solvent. Or another way to say this is the properties of a solution, that is a solvent with solutes dissolved in it, will be different than the properties of the pure solvent without the solutes added. For example, the presence of solutes lowers the vapor pressure. The presence of solutes increase the boiling point, and the presence of solutes in a solvent depresses or lowers the freezing point. All right, so the solution will have a lower vapor pressure, higher boiling point, and lower freezing point than that of the pure solvent. And the reason for this, what causes it, are the intermolecular attraction between solute and solvent. All right, and we will explore this a little bit more in tomorrow's lecture, as well as talking about osmosis, and that will kill off chapter 8. So we're going to go ahead and put a pin in it here. I will return at 3, and we will hit up office hours, first office hours of the week. We'll be live at 3 o'clock. Thanks, dudes, and I will catch you all in about 30. Later.